Can you all hear me okay? We good? Okay.
Yes.
I want to start out with one more example of a geometric series, and then we're going to move on to the next two series in this section, and then maybe if we're lucky, move into the next section. I was looking at our calendar, and man, we're just so crammed for time here. We've got Thanksgiving holiday. We're going to lose a day. I just want to kind of let you know, if we run out of time, I might in that last week ask you to watch one of my pre-recorded lectures, just so that you have all the material. Let's see how things go. All right, so the example I want to show you here is this one. Let's say that we have a repeating decimal. Let's go 3, 2, 5, 3, 2, 5, 3, 2, 5. So we have this decimal that just repeats, right? It's got a pattern. We did something like this last time. We did 1/3 is 0.333, right? And we were able to convert that over to a geometric series and find that it converged. And then we did this one, 0.0333, and we found that we could rewrite that as a fraction. So now, kind of building on that a little bit, let's do this one. All right, so first thing we have to realize is that, you know, what our positions here on the decimal mean, right? This is how many tenths you have, how many 100ths you have. Sorry, you can't see that very good. How many thousandths you have. So another way I could rewrite that decimal. Oh, and I forgot to tell you the instructions. Write as a fraction. So I want us to be able to write this decimal as a fraction. So that means I can rewrite this as 325 over, let's see, tenths, hundredths, thousandths over 1,000 plus, and then I have another 325, but that's going to be over, let's see, what place are we in? Thousandths, this is 10 thousandths, 100 thousandths, millionths, so that's the millionths position. And then plus 325. Oh. And now I'm going to add another 3 zeros, right? Because I keep on going out by 3. Did I get enough there? 3, 6, yeah. So that's 1,325 billionths. Understand? Okay, now I'm going to rewrite that as 325 over 10 cubed plus 325 over 10 to the, let's see, 6 zeros, so 10 to the 6th plus 325 over 10 to the, I added 3 more zeros, 9th. And if I did another one, it would be 325 over 10 to the, add another 3, I get 12. And this pattern continues forever. So remember, the goal here is to try and get this to look like this. Sum n equals 1 to infinity of a times r to the n minus 1. That's what geometric is, right? So I've got that. Now, all of them have a 325. And I noticed that the power, the denominators are all powers of 10, but they start at 3 and then they continue to go up by 3 each time. So how could we generate a list of numbers that would start at 3 and then jump by 3 each time, right? That's kind of the question. So I'm going to convert this to a sum. My numerator is always 325. And then you go, someone tell me 10 to what power? I want to start at 3 and jump by 3.
3n plus 3.
Just 3n.
Oh, okay.
When we start at 1, we'll be at 3, right? And then when we do 2, it'll be 6, and then 3, it'll be 9, and then 12. You could also say those are all just multiples of 3, right? 3, 6, 9, 12, 15. But that's it right there, okay? that should generate this series. So we now need to figure out if, what A is and what R is. And we have to have our R raised to the n minus 1. And right now, the only thing that we have raised to any power is this 10 is being raised to the 3n. We'd love for that to be an n minus 1. So watch what I do here. This is all just going to be algebra. So first thing I'm going to do is realize that the 325, really, I don't have to deal with it. I can move it out front. And then I'm going to rewrite that 1 over 10 to the, or the 10 to the 3n on the bottom. I'm going to write it as 1/10 to the 3n. And that's because if I rewrite it as a fraction 1 over 10, when I raise the 1 on top to the 3n, I just get 1. That doesn't change anything. But then the 3n would be applied to the bottom, and that would give me the 10 to the 3n. So is that okay? Yeah. Then I'm going to use something else that's going to really help. I know you might be tempted at this point to say, hey, let's just do the -1 + 1 right now to make it look like -1. But the formula has n here, not 3n. So watch what I do. I'm going to rewrite that as 1/10 to the 3rd to the n. And that's just using the property of exponents that when you have, let's say, x raised to the n, but then you raise that to the m, that you multiply the powers together. So I'm looking at 3 times n here as being rewritten as 1/10 to the 3rd to the n. And that way, if you multiply those together, you get back this. So I'm working backwards from this formula. And then I'm going to actually cube the 1/10. So 1/10 cubed is 1 over 1,000. And then to the n. I'm getting closer, right? You see how I'm manipulating this? I'm getting closer and closer to this form. I need to make that an n minus 1. So here's where I do -1 + 1. Feel free to jump in with any comments or questions. So now I'm splitting this up, right? I'm looking at it as like, I'm going to do this to that power times this to that power. That's this. And I'm so close to having this now. Sum n equals 1 to infinity. I'm going to bring this 1,000 over here with that. And then I'm going to have 1 over 1,000 to the n minus 1. And there you go. We've got it. So there's a lot of algebraic manipulation here. But we know now what A is, right? A is that number. And R is that number. And what is the thing we check again for geometric series to tell if it diverges or converges? What are we looking at?
If R is less than
The absolute value of R is less than 1, right? Which it is, right? 1/1000th is definitely less than 1. So I know this converges. And I know it converges to what? A over 1 minus R, right? This is all on your formula sheet. But remember, this will converge to A over 1 minus R. That's the big kind of takeaway. If we have convergence, that's what it goes to. So I'm going to write that down. A is 325 over 1,000 over 1 minus 1/1000. So that gives me 325 over 1,000 over 999 over 1,000. And if I flip, like reciprocate that fraction, the thousands cancel, and I get 325 over 999. And you can check that on your calculator. Take 325 divided by 999, you will get 0.325325. All right, That's it. I mean, there's a lot of things in this problem. You have to convert the decimal over to the fractions added together. You've got to notice that the denominators are all powers of 10. You've got to be able to rewrite this in sigma notation. You've got to be able to try and massage this into this form. So you have to get rid of the 3 by looking at it as 1/10 third to the third to the n. And then you've got to, you know, have your hidden 0 in here, -1 + 1, split it up, and then boom, you're there. Interesting little fact here, that when you have a repeating decimal, let's say you had the repeating decimal point, let's say it was just 0.323232 forever. It turns out that if you did this again, you would wind up getting 32 over, any guesses?
99.
99, yeah. And if you did something like this, 0.3215, 3215, 3215, then that would turn out to be 3215 over 9999. Kind of interesting. In fact, let's see, if you take the decimal point 3333 repeating, right? It's only the 3 that's repeating. So following the same pattern, that should just be the thing that repeats, which is 3, over what?
9.
Just a single 9, right? And 3/9 is 1/3. And we know that 1/3 is 0.33333, right? It's kind of weird. Here's where things get real weird though. Watch this. What would 0.999 repeating be? So what's the thing that repeats?
9, 9,
And you would divide it by?
10,
No,
9.
5,
9, right? Which would just be 1.
1.
Which means
is-
that 0.999 forever is 1.
It's only if you round it off, I guess.
Well, no, if you don't, it's if you don't round it off, it is the number 1. That's what we're saying. So like if you look at a number line and you take the number 0, let's say take number 1, you start looking at numbers that are close to 1, like 0.9 is right here, right? But there's
Yeah.
another number that's even closer. 0.99 is even closer, isn't it? But there's another
Mhm.
number that's even closer, 0.999. And there's a number that's even closer, 0.9999, right?
Yes, I understand what you mean now.
But if you take the number 0.999 forever repeated, that's not the number right next to 1. That is the number 1. And that's really weird, but that's what it is, okay?
Because it's like going on, because it's repeating and repeating, is that why?
It's impossible for you to find a number in between those two. So if you think that 0.999 forever is not equal to 1, then you have to be able to find me a number in between these. And you will never find it, okay? There's no number that exists between these two, which means they're the same number. Oh, hold on a second, my phone is like going crazy. Oh, okay, got it. Weird stuff. Okay, we're not going to get into that anymore, but let's move on, yes? The next type of series, and in case you forgot, last class, I said that our goal here was to talk about 3 different types of series. Where is it? I know it's here. There we go. 3 important series. Geometric, check, got it. Moving on. Harmonic is next. I've got great news about harmonic.
Is it easier than geometric?
Oh yeah. Oh yeah. Harmonic is almost too easy. So first we need to know what a harmonic series looks like, all right? So what makes a harmonic series harmonic? Well, here's what they look like. It's the sum from n equals 1 to infinity of any constant c over any linear expression in n. Let me give you some examples. sum n equals 1 to infinity of 1 over n. That's the most basic harmonic series you're ever going to see. All right. We have a constant on top, right? Constant is 1. And then the denominator is just n. Do you agree that n is linear?
Yes.
Right? It's not squared or anything else. So that's linear. That's harmonic. Okay. Let me give you another example. Sum n equals 1 to infinity of negative 10 over n plus 2. That's harmonic because it's a constant over a linear expression in n. Another example, sum n equals 1 to infinity pi over 3n, let's 1 minus 3n. There we go. Just making sure this is never 0. Okay, that would be harmonic. We have a constant, pi is a constant, over a linear expression in n. Right? That's what a harmonic looks like. Are we clear? So here's the great news. All harmonic series diverge. All of them. Which means all you ever have to do is know that you're looking at a harmonic series. As long as you know you're looking at a harmonic series, then you can tell me it diverges. They never converge. All right? So I'm going to now try and convince you that they do. But the convincing that I'm going to give you is somewhat challenging because you're just going to have to kind of be like, yeah, I see how that would work. But that we don't have like, we're not going to go through a formal proof of it. And to do it, I'm going to convince you for this first one. Okay, I'm just going to try and convince you for the first one. So let's say we take this sum, n equals 1 to infinity of 1 over n. And the question is, does this converge or does it diverge? All right. We talked about the pregnancy test last time, didn't we?
Mhm.
Yes. Okay. So remember, the first test that you ever want to do on a series, right, is that nth term test. That was that one that looked like this. That one right there, the nth term test. We check to see, does the sequence go to something other than 0, right? Does the sequence, not the series, does the sequence go to something other than 0? So if I just focus my attention on this and I run the nth term test and I take 1 over n, I know that that goes to 0, right? If I let n go to infinity. And that tells me that this test fails, right? The test fails. Fail. Test fails. Do we all understand that? The nth term test fails here? Okay. This is the most common mistake I see when students are just learning about series, is they cannot remove themselves from wanting to take the limit of this and saying, oh, if that goes to 0, it converges. The series converges. They can't distinguish between the two ideas. Whatever this sequence does not tell you what the series does, unless that thing goes to something other than 0. So if this limit right here of this, just that, would go to 1, then we could say it diverged. But since it goes to 0, we're inconclusive, so we need something else. But I'm telling you it diverges, so here's how I'm going to try and convince you. Let's write this series out. Okay, I'm going to write it out. So I'm going to start plugging in numbers. I plug in 1, I get 1 over 1, plus 1/2, plus 1/3. I'm going to write a lot of these. 1/4. I actually should have given myself some more room. 1/5, 1/6, 1/7. I'm going to go all the way out to 16. 7, 1/8, 1/9, 1/10, 1/11, 1/12, 1/13, 1/14, 1/15, 1/16, plus ... Right? That's what this series looks like. Yeah? Okay. Now, that should be equal to So what I want you to look at now, just tell me if you agree with this or not. That is equal to 1 plus a half, right? So that's basically these two, right? Plus, I have to remember how to do this. I haven't shown this in a while. So, okay, what about, I want you to consider just these two right here. Okay, just those two. If I asked you to put those two together and get a common denominator, what would that be?
12.
Common denominator would be 12. So we had 12 on the bottom. What would the numerator be?
7.
7, right? So
Yes.
7 over 12, agree?
Mhm.
Okay. So that's plus 7 over 12. Now what I'd like for you to look at is not the next two, but the next 4 together. Okay? Now, we could get a common denominator between those, couldn't we?
Mhm.
We could. But I want you to think about something here for a second. This one is 1/8, right? Do you agree that this one right here is bigger than 1/8? And this one here is bigger than 1/8? And this one here is also bigger than 1/8?
Yes.
Aren't all 4 of those bigger than 1/8? Yes? So I'm gonna change something up here. Remember how I put an equal sign here? I'm gonna change this to a greater than sign. Because what we're saying here, what I'm trying to convince you is that this sum right now, what I'm doing here, this sum, is now it has to be bigger than 1 plus a half plus 7/12. Here they're the same, right? Here they're the same.
Mhm.
But if I say that the next few terms are 1/8 plus 1/8 plus 1/8 plus 1/8, and you're telling me that each of these guys are bigger than these guys, then this sum would have to be bigger than that. Are you following me or not?
Mhm.
Okay, but what is 1/8 plus 1/8 plus 1/8?
Like 4/8.
That's 4/8, and 4/8 is a half, isn't it?
Yes.
Okay. Okay. All right, plus. Now, I want you to look at the next 8 terms. What's the smallest number in this list? The smallest one.
1/16.
1/16.
Over 16. So that one's bigger than 1/16. 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 They're all bigger than 1/16, aren't they?
Mm-hmm.
Which means that the sum in green should be bigger than me just doing 1/16 8 times. How important is it that I've said 8 times?
It's 1/4.
Is it?
1/4.
One,
Yes. Before.
hold on, not 1/4. Not one. There, 1, 2,
Well, half.
3, 4,
They're
5,
half.
6, 7, 8. Yeah. So I took 8 of them, right? If I take 8 of these, that's going to be 8/16, which is another half, isn't it?
Okay.
So they're getting bigger.
Well,
If you add,
so how many, if I said I stopped here, but how many should I go out on the next to convince
16.
you of the next
16.
piece? What's
12.
that?
32.
16.
16. So we went, first we did 2, then we did 4, then we did 8. Now I'm going to go, if I went out the next 16 of these, right? What I could say is that those 16 added together would be bigger than, right? Should be bigger than me putting 16 of those together. And they would be 16 of the, they would all be 1/32, because if you go 16 past 16, you'd be out at 1/32. So that next group of 16 would be 16/32, which would be a half. So what I'm building up here is something that looks like this. 1 plus a half plus 7/12 plus a half. Then I'm going to have another half. Then eventually I'll have another half. And then eventually I'm going to have another half. Then eventually I'm going to have another half. And do you see that now what's happening is that I keep on adding on a half, a half, a half, a half?
Repeat
You
it.
see
Yep.
that those aren't getting smaller now? And so this is gonna blow up. This thing, this whole thing, when you add up, if you added 1/2 plus 1/2 forever, right? That should go to infinity. And this sum in green has to be bigger than that. And the only way you're bigger than infinity is if you're infinity yourself. Okay, so like I said, it's not a formal proof, but it just shows you how you could at least convince yourself that it's true. All harmonic series diverge. That's it. Nothing more to say about harmonic series. The key for you will be identifying that you're dealing with a harmonic series. All right.
Mhm.
Constant over linear. That's all you're looking for. Constant over linear. All right. Next thing. Telescopic. Or also known as collapsing series. All right. Okay, so let's take a look at this series. And hold on, let me think about this. Yeah. So let's take a look at this series. Sum n equals 2 to infinity. All right, I started at 2 for a reason. Of hold on. I want our numbers to work out nice here the first time. I had this ready. Hold on. My printer ran out of paper, so I couldn't print this out before class. I forget that I'm not in my office where I have an infinite supply of paper. I've got to order some. Where is it? There we go. Okay. Yeah. Yeah, I guess you know what? Let's start it at 1. Let's start it at 1 just so you're not freaking out. Okay, let's do this one. 1 over n times n plus 1. All right, so when we look at that, let's rule some things out. First of all, nth term test, the pregnancy test. What does the pregnancy test tell us? We look at just this. Where does that go if n goes to infinity?
0.
0, that tells us nothing, right? So we can throw the nth term test out. Is this a geometric series? What's the thing about geometric that kind of leads you to, like, what is it that you have to recognize in a geometric?
Linear. Has to be a linear.
Exponential
No,
n minus 1.
Not harmonic, geometric. Say it.
No.
The constant? No, not the constant, the
The
power?
exponent, n is in the exponent.
The n here, right? The index that we use when you're dealing with a geometric series, the n is always up in the exponent, right? That's what lets you kind of think maybe I have geometric. Here, the n is not in an exponent. Do y'all see that? And I believe, if I'm not mistaken, I could be wrong here. Does the formula sheet tell you that? No, it doesn't. Yeah, it doesn't say that. I wish it would say here, you know, if your n is in your exponent, this is a good thing to use, but oh well. Okay, so we don't have this, do we? Our n is not in the exponent. Okay, so now we think maybe it's harmonic. Well, what's the problem?
That's not linear. That's
Yeah,
quadratic.
that's not linear. If you distribute the n through, you're going to n squared plus n. That's quadratic. So it's not linear, so it's not harmonic. You see? So we don't have geometric, we don't have harmonic, and it failed the nth term test. So maybe we can start writing out the list of numbers, or not the list of numbers, the sum. Maybe we can actually get a feel for what this sum is doing. So let's plug in 1. Plug in 1, what do we We get 1
One
half,
over-
right?
Yes.
Plus, now let's plug in 2.
6, 1 over 6.
1 over 6, let's plug in 3. 1/12, right?
Mhm.
Plug in 4,
1 over 20.
1/20, right? Plus dot, 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 dot. Yeah, so there it is. That's what it is, right? That's what it is. Right now, it does not appear that there's much we can do, all right? It's not geometric, it's not harmonic. We might say, well, hey, maybe we can find a formula that creates the list of numbers. Well, we have the formula. There's nothing to find. We have it. We just don't have a way of knowing what happens here. Unless we do something that might seem a little unnatural. But as soon as I do it, you're going to be like, okay. Does anyone know where I'm headed with this? You see what I'm
Partial
doing?
fraction.
Yep, I'm doing partial fractions. I'm going to do a partial fraction decomposition on this. And so what I'm trying to do is see if I can turn this expression into the sum of 2 fractions. Now, let's do that. So we've done this before, right? Like, in fact, I'm not even going to go through it, okay? I'm not even going to go through that work. I'm going to trust that you know how to do that by now. And I'm just going to tell you that what happens is that this becomes this. One over n minus 1 over n plus 1. So we have pulled this apart into partial fractions. Okay? Or we have done partial fractions and pulled this apart. Now, right now, you might be very tempted to look at these individually and be like, hey, that's harmonic and that's harmonic, right? Because now aren't these both harmonic?
Mhm.
So this would diverge and this would diverge, right? If they were harmonic,
Yes.
but you can't. And here's why you can't. There is a theorem that we have that I need to give you, and I'm going to do it on different pages. I don't want it to get in the middle of our work. Let's say that you have a series. This is a theorem. Doesn't have a name, okay? Let's say you're taking the sum of a series and you're doing some sequence plus or minus some other sequence. So that's kind of what we have right here. We have the sum and we have some sequence 1 over n minus some other sequence 1 over n plus 1. So the theorem says that if you've got the sum of 2 sequences either added or subtracted together, yes, you are allowed to split this up into 2 different sums. Okay, so you can look at them individually, all right? All right, you are allowed to do this, but only if the sum, that sum, and that sum converge. So this idea of being able to split something up into 2 pieces like this, take a sum that has 2 things being added or subtracted and split it into 2 sums, is only valid if these 2 things by themselves converge. All right, if one of these diverge, you're not allowed to split them up. So here I have the sum, I've got 2 things subtracted. I am not allowed, in this case, I am not allowed to do them individually. I am not allowed to do this because by themselves they diverge, right? That's harmonic, harmonic. All right, so you can't do it. Can I proceed? All right, so we're not allowed to do that. So what are we gonna do? Well, let's write this out again, okay? Let's write this out again. What is this? So let's plug 1 in again. What would happen if I plug in 1? I would get something like this: 1 over 1 minus 1 over 2 plus, now I'd have to plug in 2, so I get 1 over 2 minus 1 over 3. And then plus, now I get 1 over 3 minus 1 over 4. Are you all following what I'm doing here?
Mhm.
Plus, the next one would be 1 over 4 minus 1 over 5 plus dot, dot, dot. That would keep going, right? Do y'all see it? You'll see what's going to happen.
It is never going to be positive or 0.
To
Mm,
alternate.
It's going to turn into the first series.
mm.
Wouldn't it cancel out Just-
Ah,
the fractions?
yeah, look at these things, right?
Are they going towards 0?
Isn't this negative 1/2 going to cancel out with that half? And isn't this negative 1/3 going to cancel with that 1/3? And isn't that negative 1/4 going to cancel with that 1/4? And isn't that what it appears going to happen the rest of the way? Yeah.
So it converges to 1?
Well, okay, it looks like it, right? It looks like it is going to, but we have to show it in a more formal manner. This step right here is just so that we recognize that when we rewrite this, when we take it from this form to this form, just by doing partial fractions, we actually see something good happening. See, up here, I can't tell you what that adds up to be because it just keeps on adding something each time. On the second form, this way, I actually see a lot of things are going to just cancel each other out, right? A lot of things are going to cancel each other out. So how do we proceed from here? I'll tell you right now that on your test, if you do this on your test and tell me the answer is 1, I'm not going to give you full credit for this. I'll give you a little bit because you did partial fractions and some other stuff. But if you tell me the answer is 1, you will have missed out on the most important part of this problem, which is the next step, okay? This is all just preparing ourselves for this next step. So I'm going to ask you to recall from last class, when I first started talking about series and I started talking about convergence, here's what I said. I said, when we have a series, we're taking a sequence and we're adding up all the pieces forever. We call that an infinite series. Then I introduced this idea of partial sums, where I said we could first just look at taking the first number, that would be some number, whatever it is. And then the next piece, S sub 2, this partial sum would be the sum of the first 2. S sub 3 would be the sum of the first 3. And generally speaking, S sub n would be the sum of the first n of these, right? That's what the partial sum meant. And then the next thing I said was, if that sequence goes to S, if it converges, then we will say that the infinite series is equal to that S. This step right here, do not forget what that means. We took the limit as n goes to infinity of the partial sum. That's what this means. To say that this goes to S means that when we took this limit, it went to some value S. That's what we have to show in order to figure out what an infinite series converges to. So we need to figure out what this is right now, okay? We have to figure out what is that limit. So that means I'm going to come back to this, and I'm going to ask us to write down what is S sub n. What is it? Well, isn't it this right here, but stopping at n? Like instead of stopping at infinity, right, which means you keep going forever, instead of stopping at infinity, doesn't it mean take this sum and stop at n, right? Yes, yes. Stop at n. So what I'm going to do is I'm going to take everything I just wrote here, I'm going to take it, but I'm going to stop it at n. Okay, so watch me do this. It'll be 1 over 1 minus a half plus 1 over 2 minus a third plus 1 over 3 minus a fourth plus dot, dot, dot. And then where did I say I'm going to stop?
N.
At n. So pay attention. I'm going to leave myself some space. At the very end of this, I'm going to have 1 over n minus 1 over n plus 1. Wouldn't that be the very last one? If I plugged n in, right, to this formula, I get this, right? That's what I get if I plug n into that formula. That's the last piece. What would the one right before that be? What would the one right before this? So this is me plugging in 1. This is me plugging in 2. This is me plugging in 3. This is me plugging in n. This would be me plugging in what? 1 less than n, right?
Mhm.
N minus 1. So what happens if you plug n minus 1 into this formula? You get 1 over what?
N minus 1,
N minus 1, and then minus, what would this one be? 1 over
1 over n.
1 over n, because you're going to go n minus 1 plus 1. What would the one right before that one be? Well, now you're going to plug in n minus 2, aren't you?
Yeah.
And so what happens here?
1 over n minus 2 minus 1 over n minus 1
minus 2 minus 1 over n minus
minus
1, right? Because you're putting n minus 2 right here, and you get n minus 2 plus 1, that's n minus 1. And I can keep going backwards, right? But I'm just going to put another plus in front of this and then just leave the dots. So what I've done is I've written out the nth partial sum, haven't I? I've written it all out. Now, and only at this point, I'm going to start canceling things out. So I think that this negative 1/2 cancels with that 1/2, right?
Mhm.
I think that negative 1/3 is going to cancel with that 1/3. How about this negative 1/4? Is it going to go away? Is that negative 1/4 going to go away?
Yes.
Yes.
If we keep going,
Because
yes.
the 1/4 should be in the next one, right?
Mhm.
Okay, so I know that that one's going to cancel out with something in that dot, 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 right? The only thing that didn't cancel up to this point is that 1. That 1 is still there. Everything else went away. Now, let's move on to these other parentheses. Maybe we'll start from the back. What cancels here? This negative 1 over n will cancel with that 1 over n, right? So that's gone. Look at this right here. This negative 1 over n minus 1 cancels with that one. That's gone. How about this one? 1 over n minus 2. Will it go away?
Yes.
Yes? Okay, what is it canceling with?
With the one before.
The one before it, right? Something in there. The only thing left, the only thing that didn't have something to cancel with was this one, right? This last one, because this one needs something over here, but there is nothing over here, right? There's nothing left for it to cancel. So that one stays. Oh, shit.
But if you go reverse, then doesn't it mean that this cancels with 1 over 1?
This one right here,
Yes.
this doesn't cancel with anything because, okay, so let me say this. Listen what I'm saying. There's a pattern that we've established, right? There's a pattern that we've established with canceling. And here's the way I'm going to describe it. When we look at each of these parentheses, the second number, right? The second number in the parenthesis cancels with the first number in the next parentheses. The second number in the parentheses cancels with the first number in the next parentheses. Yes? So if you're a second number, right? If you go anywhere in this list and you just pick me a second number in the parentheses, I know that in order for that second number to go away, there must exist a number in the, I must have a first number in the next parentheses. So that means I have to have this guy, yes, right? If you're a first number anywhere in here, you need a second number in front of you to cancel. Is that making sense?
Mhm.
Mhm.
So look at this green one. This is a first number in the parentheses. In order for it to cancel, I have to have a second number in the parentheses in front of it, but I have no parentheses in front of it, so it doesn't cancel. At the end, the green one, it's a second number in a parenthesis. So for it to cancel, I need the first number from the next parenthesis. I know that right now you might be saying like, why are you making this so complicated? It doesn't need to be as complicated. Look, I see they cancel, like chill out, right? That's because in the next example I show you, the pattern's not going to be so clean. The cancellation might be happening 3 parentheses down. It may not be right next door. And so we have to establish the pattern. It's more important to establish the pattern than it is to actually see the cancellation. You'll see, but there's a reason why I'm kind of like over explaining this a little bit. All right, are we good though? Do you see that the greens are the only thing left?
Yes.
Okay, so that means that S sub n is equal to 1 minus 1 over n plus 1. And what is it that I said we need to do with this once we come up with this formula? What were we supposed to do with it? From last class? Once we figure out the formula, we need to
Say
take the
that.
limit of it as n goes to infinity. And whatever that answer is the sum of the original series, the infinite series. So now I'm just going to take the limit as n goes to infinity of 1 minus 1 over n plus 1, and this is 1.
So in this case, we're saying that we're going to take the limit to prove that this converges. Is that what it is?
We are, whenever we look at an infinite series like the original problem,
Mm-hmm.
we know that this piece in here, this sequence in here, creates a list of numbers that we're adding together, right? This is it, right? And the partial sums, right? S sub 1, S sub 2, S sub 3 would be like, so S sub 1 would just be 1/2. S sub 2 would be those two added together. S sub 3 would be those 3 added together. S sub 4 would be the first 4 added together.
Mm-hmm.
If we can come up with a formula, for S sub n, that would mean a formula for the first n added together, right? Which we did. We came up with a formula for the first n added together. Here it is. Then all we have to do now to figure out what the full series is, the full sum forever, is to let n go to infinity. And so we let n go to infinity here, and that tells us that that sum has to converge to 1.
Okay.
I hope that that makes a little more sense.
Mm-hmm.
Okay. All right. Now, why did they call this a collapsing or telescopic series? Here's the way I picture it. I picture it like, I don't know, like a bridge between two things. There's a little suspension bridge, okay? There's my little suspension bridge across. Maybe there's a little river here running underneath, right? And what just happened to this sum? Look at this sum right here.
It kind of collapsed in on itself.
Yeah, like everything on the inside, all that collapsed, right? Everything, the bridge collapsed, everything fell into the water. The only thing left was some shit at the ends, right? Everything else just collapsed. You could also think about it this way: old school telescopes. The old school telescopes, right? They would get them, they would pull them out. You know what I'm talking about? They pull them out, and they look around, and they close them up. So what happens here is when you close something like this, all the inside goes away, right? And you just get the two ends come together. That's the idea. All right, let's look at the next one. All right, here we go. This will be, I don't know, will this be our last example? These take a while. Yeah, I might do 2 more. But you know what? I don't want to do that one. I've already done. So let me just do something real quick. I want it to work out nice for you. Okay, here we go. Sum. Yeah. N equals 3 to infinity. Don't freak out about the 3. 2x minus 1 over x squared minus x minus 2. I don't know why I used x, everyone. Sorry. Minus n minus 2. Okay, there we go. So there's a reason why I started my series out here at 3, and you'll see in a minute, all right? So let's just start running through the ideas here. First, nth term test, right? Pregnancy test. Is anybody offended by me calling it pregnancy test? Y'all okay with that? All right, so that fails, right? You can just see that this right here, we would eventually do L'Hopital. If we did L'Hopital, we get 2 on top. We'd have something, it would go to 0. So we can, that's not gonna work. Is it geometric? So do we see n up in the exponent? Nope.
No,
Okay. Is it harmonic?
no
Definitely
idea.
quadratic, right? So the only thing we really have at this point is probably the telescopic or the, collapsing. So I've got to do partial fractions. So I've got to come over here and say, okay, 2n minus 1 over n squared. Oh, I need to factor the denominator. That would be n minus 2n plus 1. Right, that's what that would be factored. And do you see now why I started at 3? Because it would be impossible for you to ever plug 2 into this. Because if you plug 2 in, you'd get division by 0, which would be undefined. So that's why I started the series at 3. That's okay though. I mean, it's not going to affect the convergence or divergence. So then I'd have to do, let's see, a over the linear plus b over the linear factor. And then you go find a and b, right? Now I've already done this for us. Oh, crapola. Shoot, hold on, everyone. I think I hit the wrong button. I did. Shit. Okay, no, I can fix it. I can fix it. I'm going to recover myself here. I hit the wrong button on my thing. It's all right. Just change the numerator. It's going to have no impact on anything we've done. Change the numerator to -3. Does that change the nth term test? No, right? Does it change that it's not geometric? No. Doesn't change that it's harmonic. What it'll do is it'll make this work out the way I need it to work out, okay? So we go through our partial fractions, not gonna show this, okay? Not gonna show this, but I can tell you that here's what this will turn out to be. You would wind up getting that A is -1 and you would get that B is +1. Okay, that's what you would get. So that means that this sum can be rewritten. Sum n equals 3 to infinity of -1 over n minus 2 plus 1 over n plus 1. Y'all okay with this? All right. Now at this point, you should already be thinking, hey, this might be telescopic. Okay, you should already be thinking that because you've done partial fractions, right? So that means you need to write out what this sum is and see if you can find a pattern. So I think I'm going to do this on the line below. So start plugging in values for n, and where are we going to start?
3.
3. Okay, be careful. Start at 3. So if I plug in 3, I'm going to get -1 over 3 minus 2 is 1, okay, plus 1 over, I'm plugging in 3. 3 plus 1 is 4, so 1/4, okay. Plus, next one. We're now plugging in 4, right? So here we plugged in n was 3. Now we're going to go n is 4. So when n is 4 in there, -1 over 2 plus 1 over 5. Do y'all see that nothing cancels here?
Yes.
Okay, keep going. -1/3 plus 1/6. Anything cancel?
No.
Nope. Okay, keep going. -1/4, 1/7. Anything cancel? Ah, there it is. You see it?
Yes.
See
Negative
this
1/4.
guy right here, +1/4 is going to cancel with this one. Okay, let's go. Let's keep going. Let's do another one. Plus. Okay, next one will be -1/5 plus 1/8. Let's do another one. -1/6 plus 1/9. I'll do one more because I have a little more room here. -1/7 plus 1/10 plus ...
So I have a question here.
Yep.
So why is the 1/4 is canceling like so far away while the other ones are like now almost next to like, you know what I mean? Like they're
Yeah. The previous example, I gave you a problem on the previous one, right? I gave you a problem intentionally.
To prove a
That-
point.
Cancellation happened right next to one, just because it was our first example. But telescopic series don't have to cancel like that. What we need to be able to discover is that there is canceling happening. Doesn't matter where it is, because look, there is a pattern here. What's the next thing that would cancel in here? This 1/5 and that
1/5.
-1/5, right? And then the next one that would go would be that 1/6 would cancel with that -1/6. And then we have that 1/7 would cancel with that -1/7, right? So if you were to try and explain to me the canceling that's happening here, does anyone want to go for it to tell me like in words how you could describe what's happening?
like it's canceling every third bracket.
Every third. Okay, and what's canceling?
The second.
The second to the
Okay.
first.
The second number in a parentheses cancels with
The first.
the first number
3
in the
terms away.
parentheses. How many away?
3 terms away, right?
3 away. 3 down. I'll say 3 down. So let me see if that makes sense. If I go and I'm just going to randomly pick the second number in a parentheses. There, I'd pick that one. That should cancel with the first number 3 down. So here's 1 down, 2 down, 3 down. The first number that works, right? See how that works? Now you should also be able to do this backwards. You could also say this, that the first number in a parentheses cancels with the second number 3 up, right? Upstream instead of downstream.
Mm-hmm.
Okay. All right. Good. We've established the pattern. We've established the pattern. Now we have to write S sub n. So what is the nth partial sum? Leave yourself plenty of room here. So that means I need to write this out, right? But I need to stop at n. And this is in my way. So I'm going to take that and move that over here just so I can move up. I want to be able to see the series. All right, here we go. So I'm gonna write a little bit smaller here. It's going to be -1 over 1 plus 1/4 plus -1/2 plus 1/5 plus -1/3 plus a sixth plus negative 1/4 plus a seventh plus dot, dot, dot. That should be enough because I can see at least one of the cancelings. Do you want to go one more? We can do one more. I'll go one more. Negative 1/5 plus an eighth plus dot, dot, dot. Now, go all the way to the end, way over here to the end, and tell me what the very last one's going to look like. Well, shouldn't that just be this formula? It's
Yes.
just this formula. Okay, so it's negative 1 over n minus 2 plus 1 over n minus 1, or sorry, plus 1. That's what would happen if I plug n, right? That's what happens if I plug in n. What would the one right before that one look like? So instead of plugging in n, now we're plugging in n minus 1 goes in. So it should be negative 1 over what?
N minus 3.
N minus 3 plus 1 over n, just n, right? Because it'll be n minus 1 plus 1. Now we plug in n minus 2, and that gives you negative 1 over n minus 4 plus 1 over n minus 1. And then the one before that is negative 1 over n minus 5 plus 1 over n minus 2. And then before that, I'm just going to have the dot, dot, dots in here. Any questions? Second numbers in parentheses cancel with first numbers 3 down. Okay, so let's start with this 1/4. That's a second number, right? It should cancel with the first number 3 down. There it is. That's gone. Let's just take care of all these second numbers. This second number here in this parentheses should cancel with the first number 2 down. There it is. Boom. They're gone. What about the next second number, 1/6? Does it cancel? Yeah, because there is a parentheses in there. It's somewhere hidden in my dot, 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 but it's there, right? Something that it cancels with. Same with the 1/7. It cancels with something in there. Same with the 1/8. It cancels with something in there.
Okay.
Everything else that I have here, anything that didn't cancel, specifically negative 1, negative 1/2, and negative 1/3, those did not get touched because these are first numbers, right? And in order for these first numbers to cancel, there has to be second numbers 3 upstream, right? But there's nothing to the left of this. So those 3 numbers are preserved, aren't they?
Yes.
Okay, using the same logic, go to the end and start trying to figure out what happens to these. And I think for this, I'm going to start with the second numbers. No,
From right to left?
I'm going to go right to left. So I'm going to be looking at the first numbers. The first numbers should cancel with the second numbers 3 up. 1, 2, 3. Is it there? Yep, there it is. That should cancel out. Does this first number cancel? 1, 2. I didn't put enough in here, but it's in here, isn't it? Somewhere in there. This guy should cancel with something in there. Does this one cancel? Negative 1 over n minus 4. It's a first number, right? Should it cancel or no?
Yes.
Yes, because that should cancel with something that's in my dot, dot, dot. How about negative 1 over n minus 5?
Yes.
Yes, that should cancel with something upstream.
So
Let's
how
look
do you
at-
expect,
How do I what?
how do you expect us to show all this? Because I know I ran out of space.
Get bigger paper? I don't know.
Write all the
Get bigger
terms?
paper, write smaller, I don't know. Yeah, it's a lot. I mean, there's a lot you have to show here, right?
So would it be expected from us that if we see a pattern, we should prove it at least twice or 3 times on each end? Is that the way it works?
I always like to see it happen twice. So up here, see how we did it more than one time. We saw it did, once, twice. You need to show it at least once, okay? At least once. But if you're convinced of it, go with one time, that's okay. If you're absolutely convinced, but if you have any doubts, just write it out and make sure you see it happen at least twice.
Okay.
What's still here? This guy here and this guy here and this guy here, those are all second numbers. And second numbers need first numbers 3 down, and there's nothing else down, is there? There's nothing else down there. So we are done. We have a formula for S sub n. It is -1 minus a half minus a third plus everything in green on the other end. And now what?
Limit.
Limit. Let's see what happens when n goes to infinity of S sub n. I'm not going to rewrite it all. Let's just look at what happens. That goes to 0, that goes to 0, that goes to 0. These 3 go to 0. And so we truly do have the collapsing happening here. And we could get a common denominator of 6. -6 minus 3 minus 2 over 6. I believe this comes out to be -11/6. Somebody can check my arithmetic on that, please. -11/6. All right.
Where can we apply these numbers on? Statistics or?
No, I mean, this is just this right here. Everything you're seeing right here. This is not so much the application, in my opinion, as it is the getting used to the idea of seeing things like this and seeing how things patterns and cancellation and the way that sums work and how you can manipulate some. See, when we first started this, if we would have started writing out the numbers, we would never have seen any cancellation ever, because we would have said something plus something plus something plus something. The partial fractions is just a rewriting of the expression in a manner in which now it's the same sum, but now because of the way we've rewritten it, we can establish a pattern of cancellation. This is just showing you how we can make sense, I guess, out of things that may appear initially to be something we could never figure out. That we do have ways, you just have to keep like attacking it. So it's, I don't know if that's helping you. I know you're probably asking more for a real world application. And I think my answer to that is going to be ultimately what this leads us to. Like, we have to have all this in place before we can actually get to our ultimate goal, which is to be able to represent any function as in its power series. That's the main goal.
Because I see this, but I know this does not apply to this example that I have. But maybe some of this stuff could be related to, let's say, write bingo cards. So that way you only get one winner when somebody wins. If you organize the numbers in a certain way, I think you can, again, I don't know if that applies to this, but if you can arrange the numbers.
Yeah, I'm sure that there's all sorts of, the more you start to analyze the world around you, the more math you start to see in it, you start to understand the complexity of everything. And you can see a lot of different types of math and a lot of different things. Yeah.
I have a question.
Yeah.
So on the first example, we only had one of each. So there was one on the left side and one on the far right left over. And for this one, we had 3 on the left and then 3 on the right. Is that because we started at n equals 3? Does that affect this?
That's a great question. Actually, it does not have anything to do with the fact we started at 3. It has to do with the fact that if you were to just think of a number line, and if I tell you that's n, right, then n plus 1 is right here, and n minus 2 is right here. And so the distance between those two numbers will be 3. And that's why you had 3 at the front and 3 in the back.
So that was just like a coincidence.
It was a coincidence. So what I'm saying is if I had changed this number down here, let's say I'd made that n plus 3 instead of n plus 1, your pattern that you're looking for, right? You know how we said this was in the problem we just did, we said it was 3 down. Well, if I change that to a 3, guess how far down it would be?
5 away.
It'd be 5 down.
Okay, so we can look at that and kind of like estimate how far we're gonna
Yeah,
go before
exactly.
you're doing it. Okay, that makes sense.
Yeah. Now, I don't think in all my years teaching that I've ever told my students that you can do that. In fact, that's how I make the problems. I choose how far away I want my factors to be from one another. And so like if I would have given you one, let's say it broke down to be 1 over n plus 1 minus 1 over n minus 1, then your pattern is going to be
2?
Next to
2
each
down,
other.
right?
Oh.
It's going to be 2 down. I would never give you something like this. That I'd never give you, because your pattern would be 14 down, and then or who said earlier there's not enough paper. That wouldn't be enough paper, right?
So
I would-
by looking at the
Wait.
problem, we can guess how, like the factors.
It's gonna be
Oh
14.
yeah, the factors tell you everything about how far apart how far down the canceling is going to be. Tells you everything, and that's why the first problem I gave you, this one right here. Look at the factors. N and n plus 1, right? They're 1 apart. These are 1 away from one another, and that's why the canceling was 1 away. That's cool. I don't think in all my years that I've ever shared that with class, but I mean, you had a good question, CJ. I mean, looking for a pattern in that, that's where it is. Okay, now the danger here, I think, again, is that students will do just this step right here. Okay, students will do just this, and they'll go, okay, like this stays, this stays, this stays, everything else cancels. So I'm just gonna, my answer is gonna be -1, -1/2, -1/3. If you do that, I won't give you full credit, not even close, because you've missed the most important part. And as soon as you start to argue with me that, well, I know those are gonna go to 0, I can give you an example where these don't go to 0, okay? Where you actually have divergence. So it is possible to have divergence. You can have something at the end where these pieces out here actually go to infinity. So then it diverges. So then what you do is you try and shortcut and just give me the first 3 numbers, and then I catch you. I'm like, aha, you never saw what this was. You know what I'm saying?
That's half the work.
Yeah, it's half the work at least, right? Okay, so let's look at one more. And let me see, does this one diverge or converge? This is an example, okay? Sum n equals 1 to infinity of natural log of n plus 1 over n plus 3. I'm just going to let you think about this for a while. I always like to give you at least a minute or 2 to contemplate once we've done a few of these, right? So think about it. I'll be back. question to self, did you run the Nth term test on that or not?
It's infinity over infinity. If I
Right,
do
So
then
L'Hopital on that would give you what?
n over 1 over 3.
1 over 1.
1 over 1. Derivative
Oh, yeah.
top.
Oh,
And
okay, yeah.
what's natural log of 1?
0.
Okay, so what would that tell you?
That it failed.
It failed. Okay, so I just want to make
Yeah.
sure that would be something you would want to do initially to not get too far ahead of yourself on these things, right? You can get lost if you go down the wrong road, but Nth term definitely fails here.
What about linear over linear? Because it's, I know for a fact that the denominator is linear.
Yeah, the only thing we have is harmonic, which is constant over linear. And then on top of that, even if that was like 1 over n plus 3, even if it was, it's still not harmonic because of the natural log. The natural log kills off all hope of you saying it's harmonic. If that were just n plus 1 over n plus 3 without the natural log, it would still not be harmonic. But what would it be? Would that converge or diverge? Would that converge or diverge?
So the first thing is I would start plugging in numbers, I think.
Would it converge to 1?
What converges to 1?
N plus 1 over n plus 3?
So this goes to 1, right? This goes to 1. What happens if this goes to 1? What happens to the series?
It doesn't, it diverges.
It diverges. See, this again is where you have to be careful. Look, run the Nth term test on this. The Nth term test, you take this, you take the limit as n goes to infinity of n plus 1 over n plus 3. That equals 1, and that's not 0. The pregnancy test was successful, okay? So Chris, I think you responded. That's the thing that you want to try and make sure you can get straight. Everyone can get straight in their minds. The sequence, if the sequence goes to 1, that doesn't mean that the series goes to 1. But if the sequence goes to 1, I can tell you that the series diverges. It's when the sequence goes to when the sequence goes to 0 is when I don't know anything about the series. Okay, let's get on this one. This is
But didn't it fail the first?
what, this one?
Yeah,
Yeah, it failed the Nth term test.
because, okay, I understand.
It failed the Nth term test. It's not geometric. It's not harmonic. So if we start writing things out, right? If we say, oh, this is equal to, let's see, if we plug in 1, we get natural log of what, 2 over 4 plus natural log of 3 over 5 plus natural log of 4 over 6. Do y'all see what I'm doing? 5 over 7 plus ... That goes forever, doesn't it?
Mhm.
And there's nothing here. There's no subtractions here. So there's no way I can get this telescopic action to happen.
You can use
Unless,
the rule of natural logs.
yes, which is,
ln n plus 1 minus ln n plus 3.
yeah. So using properties of logs, we learned in college algebra that if you have the natural log of a fraction, that you can turn that into natural log of x minus natural log of y. That's a property of logs.
But my question is, would you have to rewrite the sum, or will it just stay?
I'm not sure what you mean by rewrite the sum.
Like, would you have to, for ln x, would you have to write a sum, and for ln y, would you have to write a sum?
Oh, no, all we're doing is rewriting the expression that's in here. Okay, so it's gonna break up. Let me write it and then you'll see, like this. Okay, so all I did was algebraically change that to this, yes? And we still want the sum of all of that. We still want the sum. Now, Renato, we cannot break this up into two. We cannot break this up into two sums. Why? Why can we not break this up into two sums? Why can we not do this?
Because we can't say it converges. Or
Actually, I think you could, I think you can tell me right now whether or not these two individually would converge or diverge.
I think they will diverge. I think
Why?
that's cannot.
Why would this diverge?
Because going to infinity.
This is going to infinity, and natural log of infinity is going to infinity. Right.
Infinity. Yeah.
That's the pregnancy test again. If you run the pregnancy test on this, it goes to something other than zero, which means that this whole thing diverges. Same with this. This goes to something other than zero, so it diverges. If these two diverge, you can't break it apart the way I just did. You're not allowed to.
Even if one diverges, right?
All you need is for one to diverge. If one diverges, you're done. Hold on a second. Okay, next thing. Let's just write out what this is. Okay, let's just write out this sum, which is going to look exactly like this, but it's going to be split up. So it's going to be natural log of 2 minus natural log of, oh no, natural log of 2 minus natural log of 4 plus natural log of 3 minus natural log of 5 plus natural log of 4 minus natural log of 6. Do y'all see what I'm doing?
Would it be a no-no if we just like skipped over doing the ln, the properties of log on the original sequence and just read that right there and just did ln 2 minus 4? So if we ignored what you have on the bottom left, the left of the equal sign, and just did
this went
ln,
from this, it went from here to here?
yeah.
Yeah, that's okay. That's okay. Now, what we need now is to see the canceling though, right? And do y'all see it here, here? You'll see that cancels?
Yes. It's
So
every
second
one.
ones cancel with first ones 2 down. Second ones cancel with first ones 2 down. Second numbers cancel with first 2 down. All right, let's write out the partial sum. S sub n is going to be natural log 2 minus natural log 4 plus natural log 3 minus natural log 5 plus natural log 4 minus natural log 6 plus ... Now I'm going to start at the end. If I go to the end, it'll be natural log of n plus 1 minus natural log of n plus 3. CJ, that's the only part right here. That part that I just did, that would be the only part that might be a little tricky for you if you did not convert this piece down to this. Is that, what does that last one look like? That would be the only part where you might be like, what? And now we go for the one in front of that, which should be natural log of n minus natural log of n plus 2. And the one in front of that one would be natural log of n minus 1 minus natural log of n plus 1. I'm so sorry, I'm trying to squeeze this in here. Natural log of n plus 1. I'll send everyone my notes at the end of class. All right, here goes the canceling. That one's gone with that one. second one, this negative natural log of 5 should cancel with something in there. This negative natural log of 6 should cancel with something in there. The ones that are preserved are the natural log of 2 and natural log of 3. Those two didn't go away. And at the end here, let's see what kind of canceling I get. That one cancels with that one. Does this natural log of n go away? This one right here? It's a
Yes.
first one, right? Yeah, so it goes away with something over here. So does that one. The two here at the end, these two at the end, those don't go away with anything, do they? They don't get canceled.
No.
Okay. So S sub n equals natural log 2 plus natural log 3 minus natural log of n plus 2 minus natural log of n plus 3. Limit n goes to infinity. Of that is equal to what?
Infinity plus infinity?
Yeah, negative infinity. Because these two, natural log of 2 is just a number, natural log of 3 is just a number. Natural log of infinity is infinity. Natural log of infinity is infinity, and you're subtracting, right? So it's negative infinity minus infinity. It's negative infinity. This diverges. Do you see now what I mean about the danger of just trying to find the pattern and thinking like back up here that you think, oh, it's just the natural log 2, natural log 3 are going to survive and everything else goes away? That can be dangerous. All right. You okay?
So what's the algebra here getting the negative infinity?
It's just taking a limit. If you just look at this right here, right?
Yes.
That's basically saying what happens to the natural log function as you plug in something that gets bigger. So the natural log function looks like this. So if we go out to
Yeah.
infinity, this function starts to grow and it keeps growing and it heads to infinity, right?
Yeah.
But there was a negative in front of it, right? There was a
Yes.
negative in front. So it's negative infinity. And same with this one.
So what about the ln 2 and 3?
Oh, that's just a number, right? That's just
Oh,
a number.
those are,
That's a number.
yeah,
Minus
yeah,
infinity minus infinity.
yeah, I'm sorry, yeah. I
That's okay.
understand.
All right. That concludes 8.2. That concludes 8.2. All right. Geometric, harmonic, telescopic. So 8.3, we're going to get some other tests that we can use to figure out whether or not, oh wait, sorry, no, I'm in the wrong section. Oops, that's 8.4. This is the integral and comparison tests. Tests. That's more than one test. So we're going to introduce 2 new tests, and I've got 10 minutes, so I'll introduce at least the first one. All right. The first test here that we're going to look at is what's called the integral test. And I'm not going to go through this in detail right now because we're going to go through it, but I'm just going to point it out. It is right here on your formulas. Here's the test. Okay, I'll make it make sense, hopefully. But I just want you to be aware that this test is available to you. So here's what the test says. It says, how do I want this? All right. It says here, oh, integral, let me make sure. Integral test. Suppose, that's how we write the word suppose in math. It's capital S with this little line here. That means suppose. Suppose that A sub n is positive, decreasing, and I'm going to add to that eventually. I'll explain that later. All right, so suppose that you have, what is this, A sub n? What is A sub n? That's a
Sequence.
sequence. So suppose you have a sequence that's positive. That means every number in the list is positive. And it's a decreasing sequence, which means they're positive numbers, but they're getting smaller and smaller and smaller. Okay? They're going down as you move from left to right. So suppose that we have that. Let f of n be equal to a sub n. If f is continuous on the interval 1 to infinity, and if f is integrable, that just means that we can find the antiderivative of it, all right? Then where did I lost my cursor. Then if the integral from 1 to infinity of f of x dx converges, so does the sum n equals 1 to infinity of the sequence. If the integral diverges, so does the series. I'll try to illustrate this, okay? Don't get so worried about copying this down. You have it on your formula sheet. But let me show this to you in pictures. The very beginning of this says, let's say that we have a positive sequence that's always going down. So let's say I have a sequence. When I plug in 1, I get some number. I plug in 2, right? I get some number that's smaller than the one before. And I plug in 3 and it gets smaller. And this keeps happening, right? And maybe it asymptotically approaches 0, right? Yes, that's our sequence, just a bunch of dots. What this test says is that if we, instead of looking at the sequence, look at the integral, okay, of this function, that whatever the area is under this curve, if that area converges, right? So if that area right there converges to a number, right, goes to a number, then the sum of the sequence should also. Does that make sense to you? Because the sequence, if the sequence is just a point here, and then this one's just a point, and then this one's just a point, and that the series is just adding up all those together, that's just like measuring how long is that one, 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 add all those lengths together, that's what the series is, then the area should also dictate how that goes. If the area is finite, then for sure the sequence, the sum of the sequence should be finite. Does that make sense? And if the area is infinite, then so should the sequence be. Or sorry, the series. Now, here's the drawback to this test. Does it tell you what it converges to? Does this say that whatever this integral is, that's what the sum is? No. It says if the integral converges, well, then you can say that this converges, but you don't know what it converges to. You can just say that it converges, all right? So this is truly
Fine.
just a test for convergence or divergence.
Thank
Yes?
you. Don't bother.
What? Oh. Okay, I don't think that was intended for us. All right, example, all right, example. Does this converge or diverge? Okay, I have to move quick because I only have 4 minutes. Okay, I'm gonna start running through things. Nth term test. If I take the limit of this, as n goes to infinity, I get infinity over infinity. L'Hopital's rule goes to 0, test fails. All right, geometric, nope, n's not in the exponent. Harmonic, nope, it's not linear. Telescopic, partial fractions, can't factor the bottom. Can't factor the bottom, it's not factorable. And so this will not go with partial fractions either. But if I look at this, is this a positive sequence? If I look at the sequence itself, can you tell me, is n over n squared plus 4, is that always greater than 0? Yeah, because I'm plugging in values of n that are always positive. So this should always be a positive number. Great. Okay, so what I can say, and remember, this right here is our a sub n, right? So I know that the sequence is positive. All right, is the sequence decreasing? So right now this says sequence is positive. Okay, is it decreasing?
Yes,
How do you know?
because there's an exponent on the bottom. N squared will always be greater than n.
Okay, yeah, so I mean, you could convince yourself of that, like, but how do we show it? I mean, you could be convinced of that, but just let's remember how we show it though. How do you show that a sequence is decreasing? You have to show that a sub n is bigger than a sub n plus 1. Remember when we did this? When we were showing the bounded monotonic stuff? Okay, so I would have to show that n over n squared plus 4 is bigger than what I get when I plug in n plus 1. Wouldn't I have to show that? Y'all see this? Okay, I don't feel like showing that. I'm actually going to show you something else, a different way of doing this, and I think you might like this. In Cal 1, how did we show something was decreasing? In Cal 1, how do you know that a function's decreasing?
The derivative is negative.
The derivative is negative. So I want you to look at this n over n squared plus 1 as a function. Okay, I know it's not, it's a sequence, but I want you to take its derivative. How do you take derivative of that? Quotient rule. I'm running out of time. Quotient rule, right? Derivative top times the bottom minus derivative of the bottom times the top all over the bottom square. This becomes, help me out, n squared plus 4 minus 2n squared. That becomes negative n squared plus 4 minus or over n squared plus 4 squared. What can you tell me about this? Is it always negative? Well, what happens if you plug in 1? What do you get? You get 3, right? 3 over a positive number. That's positive, isn't it? It's not good. But what if you plug in 2? Let's see, 2, you plug in 2, you're going to get 0 over that. That's 0. What if you plug in 3? This thing will start to dominate this 4, won't it? So eventually, not right away, but eventually, wouldn't the top always remain negative? Yes? It's not always negative, but as n gets bigger, this does stay negative. And what this tells you is that this is decreasing. Now we'll do more examples of this because I'm out of time, but you're welcome to show this is true also. I want to finish though. So after we finish this step completely, we would be able to say that a sub n is decreasing. since it's decreasing and it's positive, I can run the integral test, which means I'm going to take this sequence and I'm going to throw the sequence into an integral from 1 to infinity, but I'm going to treat the sequence in terms of x instead of n. And whatever that does is what the sequence, the series does. How would you integrate this?
Sub?
Basic U sub. Use the denominator. I'm not going to go through it, but it turns out to be this natural log of x squared plus 4. Right? And we want to evaluate that from 1 to infinity. Now, I know that that's weird because this is an improper integral, right? So we're supposed to do a limit here, but let's just kind of think through this. What would happen if I plug infinity into this? Go infinity into this. What would happen to that? It'd become infinite, wouldn't it?
Mhm.
Plug 1 in, it would give you a number. So what happens here is that this integral goes to infinity, which means that the integral diverges, right? And this test says whatever the integral does, the series does. So my conclusion would be that this diverges through the integral test. Okay, we have a lot to do still, obviously, but just in summary of the integral test, you have to look at the sequence inside, show it's positive, show it's decreasing, throw it into an integral, integrate it, that's an improper integral. Whatever that integral does is what the original series does. If this goes to infinity, that thing diverges. If this goes to a number, that thing what?
Converges.
Converges, not necessarily to any number. We don't know what number it converges to, but it does converge. Okay, do your 8.2 homework. You also have a test or something. I don't know. I went through the test. I think the test is pretty straightforward. There's a few problems on there that are a little bumpy, but there's a few on there that I think are just kind of trivial too. So hopefully it's going okay for you. Have a good day. Yeah. Anything else? Okay. Reach out if you need me. All right.
Okay. Thank
Will
you.
do.
All
Thank
right.
Have a great one.
Thank you. Have a nice day.
Bye.
Have a good day, Professor.
Yep. Do your homework. 8.2.
I have one question.
What's up?
So I was trying to graph the ln functions using the Desmos, but I think I'm running into a problem. I don't understand how to graph those functions because I was initially using by hand rather than the computer.
You're having trouble doing what? Graphing the natural log?
Not the natural log, the ones on the test. I tried doing them for the area under the curve and all that. So it wasn't like, I don't think I'm doing it correct. I don't know why. Because the way I'm doing it using my hand, which I know for a fact, it's so yeah, when I was doing the y equal nx, this one, yes.
Yeah, why didn't you just go to a computer and graph it?
I did. And the
What
only thing is,
computer were you using?
I was using my iPad,
Yeah, but what software were you using to graph it?
Desmos.
And what was wrong when you typed it in?
So like the way I'm graphing it using my hand, I think that, I'm not sure because I'm just confused why when I'm trying to do it by hand, because I like the way I'm doing it with my hand because it's more easier.
Yeah.
Yeah.
That's
So
right there.
but mine is going the other way. It's going to the negative. I don't know why.
So
Because
what do you plug in? You plug in 1.
So I get 0.
If you plug in
No,
1,
wait.
you got 0.
No. I'll get a 2. Wait, no.
When you plug in 1,
I get a 1.
you should get 1, right? So here's 1. Yeah, when you plug in 1, you get 1. When you plug in 2, you have to do natural log. It should just be natural log of 2.
Okay. So, oh, I get it. I wasn't graphing it like that. I was graphing it like ln, and then the negative x would be like reflective over. Yeah, I think
Oh, okay.
yeah, I understand.
Oh, you were
Thank you.
trying to combine these together, maybe? All right.
Yeah, I
That-
think, yeah.
That X is separated from that X. These aren't the same. These aren't both inside the natural log, right? Just this X.
Oh, oh, okay, I see now. Okay, yeah, perfect. Thank you.
Okay, no problem. Anything else? You good?